Good evening, everyone. This is the third lecture of continuity and differentiability, the second chapter in the calculus course for JEE. I am Apoorv Tandon, computer science undergraduate at IIT Kanpur. So, in the past two lectures, we've discussed essentially what it means for a function to be continuous at a point, what it means for a function to be continuous on an interval, and some specific cases of continuity. In this lecture, we're going to focus on one important application of the concept of continuity, which is called the intermediate value theorem. And post that, we're going to look at various aspects of differentiability. So let's start with the intermediate value theorem. So the intermediate value theorem, or the IVP, the intermediate value theorem. First, let's look at what the formal statement of this theorem is, and then we'll look at sort of an intuitive idea of what it really means. So the statement of the theorem is, if f of x is continuous on a closed interval a comma b, and f of a is unequal to f of b, then for any real number belonging to the open interval f of a to f of b, there will be at least one x belonging to the open interval a comma b, such that the value of the function at that point is equal to c. So essentially what this theorem is telling us is that if we have a continuous function and it's defined from some point a to some point b, the value at a is different from the value at b, then all values between f of a and f of b will be covered by the function, right? So in a more intuitive sense, let's understand it through a graph. For example, we're given a graph like so. यहाँ पे point A है और यहाँ पे कोई और point B है. ग्राफ को हम ब्लैक से प्लॉट करेंगे. मान लीजिए कुछ ऐसा ग्राफ दिया गया है. अब देख सकते हैं मैंने ये ग्राफ बिना पेन को उठाए बनाया, मतलब ये कंटिन्यूअस ग्राफ है. ए पे मान लीजिए इस फंक्शन की वैल्यू एफ ऑफ ए है और बी पे इस फंक्शन की वैल्यू एफ ऑफ बी है. अब देख सकते हैं एफ ऑफ ए और एफ ऑफ बी डिस्टिंक्ट है, दे आर नॉट इक्वल. तो ये स्टेटमेंट, ये थ्योरम क्या कह रहा है कि अगर ए पे एफ ऑफ एक्स की वैल्यू ए पे और बी पे अलग है, तो एफ ऑफ ए और एफ ऑफ बी के बीच, यानी इन सारे पॉइंट्स को ये फंक्शन कवर करेगा ए और बी के बीच में. और आप देख सकते हैं कि ये ट्रू भी है. एफ ऑफ ए और एफ ऑफ बी के बीच कोई भी पॉइंट ले लीजिए, मान लीजिए टी बिलोंगिंग टू रियल, सपोज टी बिलोंग्स टू एफ ऑफ ए कॉमा एफ ऑफ बी, उनके बीच में लाई कर रहा है. वी कैन ऑलवेज फाइंड सम एक्स बिटवीन ए एंड बी विच हैज दिस एज इट्स इमेज अंडर एफ, है ना? तो ये हमें मिल गया एफ इनवर्स ऑफ टी, द वैल्यू विच मैप्स टू टी अंडर एफ. तो ये थ्योरम कह रहा है कि अगर ए और बी के बीच में हम एक कंटिन्यूअस कर्व बना पा रहे हैं, तो एफ ऑफ ए और एफ ऑफ बी के बीच हर पॉइंट को ये ग्राफ कवर करेगा. सो दिस इज द इंट्यूटिव सेंस. इंट्यूटिव सेंस का अगर हम यही वर्ड्स में लिखना चाहें, तो दिस इज सॉर्ट ऑफ सेइंग दैट ग्राफ of f of x can be traced continuously from the point a comma f of a to the point b comma f of b. Then it must take on every intermediate value from f of a to f of b, of course possibly more than once. जरूरी नहीं है एक ही बार इन सब वैल्यूज को कवर करें. जैसे मान लीजिए टी हमने यहाँ लिया, इस पर्टिकुलर ग्राफ में एक ही पॉइंट पर एफ ऑफ एक्स की वैल्यू टी आ रही थी, पर अगर इस ग्राफ में ज्यादा बम्प्स और वैल्यूज होते तो शायद हो सकता है कि ए और बी के बीच में दो से ज्यादा या एक से ज्यादा पॉइंट्स हो जिनकी इमेज टी हो. तो यही कह रहा है कि इट टेक्स ऑन एवरी इंटरमीडिएट वैल्यू between f of a and f of b, possibly more than once. Or because we are talking about values which are intermediate to f of a and f of b, we call this theorem the intermediate value theorem. So यही मतलब है intermediate value theorem का. और ये कंटिन्यूटी का काफी इम्पोर्टेंट कॉन्सेप्ट है, इम्पोर्टेंट एप्लीकेशन है। देख के लगता है कि ये बहुत ट्रिवियल चीज है, कि ये ऑब्वियस है, पर आप देखेंगे कि प्रॉब्लम्स में काफी बार ये स्ट्राइक नहीं होता, और काफी प्रॉब्लम्स लाइक बहुत आसानी से इंटरमीडिएट वैल्यू थ्योरम से सॉल्व हो जाती है। तो इंटरमीडिएट वैल्यू थ्योरम के एप्लीकेशंस के हम दो कॉरोलरीज के बाद एग्जांपल्स देखेंगे। तो इंटरमीडिएट वैल्यू थ्योरम्स की एसेंशियली इसी थ्योरम से हम दो कंक्लूजन निकाल सकते हैं, जो हम कॉरोलरीज के फॉर्म में देखेंगे। सो पहला कंक्लूजन, इफ अ कंटिन्यूअस फंक्शन इज ऑफ opposite signs in an interval, then it has a root in that interval. मैथमेटिकली ये क्या कह रहा है कि मान लीजिए हमारे पास दो पॉइंट्स है ए और बी, सच दैट एफ ऑफ ए into f of b is less than 0. Without loss of generality, let us consider f of a to be positive and f of b to be negative. तो आप देख सकते हैं एक वैल्यू नेगेटिव है, एक वैल्यू पॉजिटिव है, और किन्हीं पॉजिटिव और नेगेटिव दो नंबर्स के बीच में जीरो लाई करता ही करता है। सो जीरो इज एन इंटरमीडिएट वैल्यू, जीरो बिलोंग्स टू द ओपन इंटरवल एफ ऑफ ए, सॉरी एफ ऑफ बी टू एफ ऑफ ए। और अगर एफ ऑफ एक्स का ग्राफ कंटिन्यूअस है ए और बी के बीच में, और एफ ऑफ ए ग्रेटर देन जीरो है, एफ ऑफ बी लेस देन जीरो है, देन देयर एग्जिस्ट एटलीस्ट वन पॉइंट बिटवीन ए एंड बी व्हिच मैप्स टू जीरो। और जब फंक्शन की वैल्यू जीरो हो जाती है, उस पॉइंट पर x की वैल्यू को हम रूट कहते हैं। तो यही ये कॉरोलरी कह रही है कि अगर किसी पॉइंट के दो साइड्स पर फंक्शन की साइंस ऑपोजिट है, तो तो उन पॉइंट्स के बीच, जैसे ए और बी हमने यहाँ लिया, ए पर फंक्शन की वैल्यू पॉजिटिव है, बी पर नेगेटिव है, ए और बी के बीच देयर एग्जिस्ट एटलीस्ट वन पॉइंट वेयर द फंक्शन क्रॉसेस द एक्स एक्सिस, वेयर द फंक्शन evaluates to zero as long as the function is continuous. So ये काफी इंपॉर्टेंट कंक्लूजन है कि मान लीजिए कोई पूछे कि इस पॉलिनोमियल के कितने रूट्स हैं, तो आपने बस वैल्यूज डाल के देखे कि +1 पे इसकी क्या वैल्यू है, -1 पे इसकी क्या वैल्यू आ रही है, और आपको पता चला कि +1 पे इसकी वैल्यू कुछ है, -1 पॉजिटिव वैल्यू है, -1 पे कुछ नेगेटिव वैल्यू है, तो आप सीधे सीधे कह सकते हैं -1 और 1 के बीच देयर इज एटलीस्ट वन रूट ऑफ एफ ऑफ एक्स ऑफ द पॉलिनोमियल। तो पॉलिनोमियल सॉल्व करने की जरूरत भी नहीं हुई टू determine how many roots or whether it has any roots. So ये काफी commonly used conclusion है from the intermediate value theorem. The other corollary that we can deduce from IVT is that the image of a continuous function over an interval is also an interval. तो इसका मतलब यही है कि द इमेज ऑफ अ कंटिन्यूअस फंक्शन, जो कंटिन्यूअस फंक्शन जो वैल्यूज ले रहा है किन्हीं दो पॉइंट्स के बीच, वो अलग अलग डिस्टिंक्ट वैल्यूज नहीं है। अगर दो वैल्यूज ले रहा है फंक्शन, तो उनके बीच सारे वैल्यूज ले रहा है, और दो वैल्यूज के बीच सारे वैल्यूज लेने का मतलब यही हुआ कि इट इज अज्यूमिंग ऑल वैल्यूज इन दैट इंटरवल a comma b, राइट, और f of a comma f of b, possibly an extended interval of f of a comma f of b. तो ग्राफ से देखा जाए, अगर a और b पर कोई ऐसा फंक्शन बनाया गया हो, a पर इसकी वैल्यू f of a है, b पर इसकी वैल्यू f of b है, हम इसके रेंज के बारे में बात कर रहे हैं। तो व्हाट ऑल वैल्यूज इज दिस फंक्शन टेकिंग बिटवीन f of a, between a and b, where a and b is the domain interval we are talking about. So image of a continuous function over an interval, a to b is the interval we're talking about here, is also an interval. So from IVT we already know that if the value at a is f of a, the value at b is f of b. It is taking all values between f of a and f of b. So the minimum interval, the minimum possible interval that it must cover, the function must cover between a and b is of course f of b to f of a. Here I've taken f of b to be less than f of a. f of b और f of a के बीच सारे वैल्यूज को ये फंक्शन कवर कर रहा है, इसकी हमारे पास गारंटी है अगर ये कंटिन्यूअस फंक्शन है। इसके अलावा ये फंक्शन इस इंटरवल के बाहर भी कुछ वैल्यूज कवर कर सकता है, पर ऐसा जो भी वैल्यू कवर करे, एफ ऑफ ए और उस वैल्यू के बीच सारे वैल्यूज भी कवर करेगा। it cannot cover an isolated point. So इस corollary का यही मतलब है कि if it is covering, if there is a continuous function between 2 points, the range of that continuous function will also be an interval. We cannot have distinct points in a set, but we must have a continuous interval as the range. So intermediate value theorem का एक example देखते हैं. Let a function f from 0, 1 to 0, 1 be continuous over its domain. When we say continuous, we mean over its domain. The domain is close 0 to 1, right? Then prove that for some c belonging to 0, 1, f of x, f of c is equal to c. And secondly, f of c is equal to 1 minus c. So देख के ये लग नहीं रहा कि ये इंटरमीडिएट वैल्यू थ्योरम का कोई एप्लीकेशन हो सकता है, क्योंकि यहाँ हमें इक्वेशंस दी गई हैं, ना कि सीधे सीधे फंक्शंस. पर अगर हम इन इक्वेशंस को फंक्शंस में कन्वर्ट कर दें तो शायद इंटरमीडिएट वैल्यू थ्योरम हम यूज कर सकते हैं. तो इसका सोल्यूशन देखते हैं. पहले वाले का, हाउ डू वी कन्वर्ट दिस इक्वेशन इनटू अ फंक्शन. सी को आप लेफ्ट हैंड साइड में ले जाएंगे, and this is a particular case of the function f of x minus x, right, at x is equal to c. So what the first sub question is saying is कि अगर कोई function g of x है, f of x minus x, इसका एक रूट c है, और फर्स्ट corollary से आपको याद होगा, we can determine a root if we know that the function has opposite signs around that point, right? So consider g of x to be the function f of x minus x. Let's see what the value of g of x is at x equals 0. It's f of 0 minus 0, f of 0, which is definitely greater than equal to 0, right? Because the range of f of x is 0 to 1, and that's greater than equal to 0. What about the value of g of x at x equals 1? This is f of 1 minus 1. F of 1 is greater than equal to 0, less than equal to 1. So when 1 is subtracted from f of x, it must be less than equal to 0, right? Like the maximum value this can attain is 0 when f of 1 is 1, else it will be a negative number. So suppose g of 0 is 0 or g of 1 is 0, we have proved the sub question, right? Because c belongs to close 0 to 1, and we have found either 0 or 1 to be the roots. That is c equals 0 to 1, 0 or 1. F of x, g of x is becoming 0. And when g of x becomes 0, it means f of x is equal to x. So if either g of 0 or g of 1 is 0, we have successfully proved the first sub part of this question. So the other case is where neither of these are 0. That is the first case, g of 0 equals 0 or g of 1 equals 0. Then just consider c to be 0 or 1 respectively. And we have proved the first subpart. The second case is that neither g of 0 or g of 1 is 0. That means that g of 0 is greater than 0 strictly and g of 1 is less than 0 strictly. This, by the first corollary, means that there exists some c between 0 and 1 open interval such that g of c is 0. And we know that when g of x becomes 0, f of x is equal to x. So g of c equals 0 is equivalent to saying f of c is equal to c for some c belonging to open 0 to 1. So using these two subcases, we have proven the first subpart of what this question is asking us to do. Now let's look at the second subpart using the same thinking process. The second subpart is asking us to find some c between 0 to 1, to prove that there is some c between 0 to 1, such that f of c is equal to 1 minus c. Okay. F of c is equal to 1 minus c here. So again, we will follow the same approach we used for the first subpart. We will take a function whose roots we have to find, like proving that f of c is equal to 1 minus c at least one c between 0 and 1. is the same as proving that g of x is equal to 0, where g of x is equal to f of x minus 1 plus c. I've taken 1 minus c to the left hand side. Sorry, plus x. F of x minus 1 plus x. So consider g of x to be this function. And now what we have to prove is that g of c is equal to 0 for at least one point between 0 and 1. Again, we will use the intermediate value theorem for this question. We will consider the value of g of x at first 0. So g of 0 is equal to f of 0 minus 1 plus 0 is equal to f of 0 minus 1 is of course less than equal to 0 by the same reasoning we used for the previous subpart, that the range of f of x is 0 to 1. So the maximum value it can attain is 0. F of 0 minus 1 can attain is 0, and otherwise it will be negative. Similarly, if we look at g of 1, that will be f of 1 minus 1 plus 1, which is f of 1. And looking at the range of f of x, we can conclude that f of 1 is greater than equal to 0. So again, we take two cases. The first case being either g of 0 or g of 1 is 0. Then we have found some c between 0 and 1 where g of c is 0. And we have proven, what the question is asking us. So let's consider the other case. The other case is that neither g of 0 or g of 1 is 0. That means that g of 0 is less than 0 strictly and g of 1 is greater than 0 strictly. Using the first corollary of the intermediate value theorem, this means that there exists at least one c belonging to open interval 0 to 1 such that g of c is exactly 0. And hence we have proved what the question is asking us, right? So this is a sort of very typical question of the intermediate value theorem, where you find that around, 1 point the function is, at one point the function is positive, at another point the function is negative, and you deduce that between those 2 points there is at least one root of the function. And then you have further constraints. If you've given a polynomial, then looking at the highest degree, you also know how many roots it has. Suppose it's a 4-degree polynomial and you've already found 3 roots. And now you just have to determine whether it has 4 roots or not. You can verify by looking at, points that you suspect will have different signs, and deduce whether it has 4 roots or not. So finding roots of polynomials is a very common application of intermediate value theorem, and converting questions like f of c is equal to 1 minus c into questions of finding roots is also a very important skill for this chapter. All right, so far we've looked at various aspects of continuity and one important application of continuity. Now we're going to move on to the concept of differentiability. We looked at the definition for differentiability, I believe, in limits and derivatives, or at least the definition of derivative by first principles. Yeah, so when we looked at the definition of derivative by first principles, we also said that we're defining it as a limit. So for the derivative to exist, the left-hand side and the right-hand side, the left-hand limit and the right-hand limit should be equal. So let's put that mathematically again. Right. So mathematically, what the first principle's definition of derivative was saying is that the limit as h tends to 0 of f of a plus h, where a is the point in question at which we're finding the derivative, should be equal to the limit as h tends to 0, as x tends to a, of f of x minus f of a by x minus a. So these are the two alternative forms of the derivative. The first one being the derivative by first principles and the second one being equivalent to the first. And the condition for existence of the derivative was that these limits exist. And if these limits don't exist, that is the left hand and right hand limits don't conquer, then the derivative does not exist. So using that same principle, we are going to define two more terms, the left hand and the right hand derivative corresponding to the left hand and the right hand limits by first principle. So we're going to call the limit as h tends to 0 of f of a plus h minus f of a over h. which is equivalent to saying f dash of a plus the right hand limit at x equals a. That is the derivative for points that are just to the right of but not equal to a, points that belong to the right neighborhood of a. And similarly, we're going to define the left hand derivative of f of x at x equals a. And now we're going to say that for the derivative to exist, the left hand derivative must be to the right hand derivative. And this will be the condition that we're going to use here on for the existence of derivative, right? So this is the mathematical condition for the existence of derivative and the definition of the derivative. What this means geometrically is that a unique tangent can be drawn at x equals a. तो हम अब तक डिफरेंशियबिलिटी के की डेफिनेशन पे फोकस कर रहे थे. अगर कोई हमसे पूछे कि क्या ये फंक्शन डिफरेंशियबल है, तो उसे हम मैथमेटिकली कैसे देखेंगे? लेफ्ट हैंड और राइट हैंड डेरिवेटिव्स को इक्वल करके. अगर मैथमेटिकली बहुत रिगरस सॉल्यूशन आ रहा है इस प्रॉब्लम का, तो एक इंट्यूटिव ज्योमेट्रिक मेथड भी है डिफरेंशियबिलिटी देखने का. वो है कि अगर उस पॉइंट पे ग्राफ पे आप एक यूनिक टैंजेंट बना पा रहे हैं. आप देख सकते हैं कि इस पॉइंट पे कोई दो टैंजेंट नहीं एग्जिस्ट करते, और इस पॉइंट पे मैं टैंजेंट बना पा रहा हूँ और एक ही टैंजेंट एग्जिस्ट करता है. ऐसा नहीं है कि राइट हैंड साइड पे एक टैंजेंट बन रहा है, लेफ्ट हैंड साइड से देखें तो एक और बन रहा है. एक ही टैंजेंट बन रहा है, तो उस फंक्शन को हम डिफरेंशियबल कहेंगे. इसकी ज्योमेट्रिक एप्लीकेशन के कुछ क्वेश्चन हम इस लेक्चर में देखेंगे. फिलहाल मैथमेटिकल और ज्योमेट्रिक इंटरप्रिटेशंस को आप मन में थाम लीजिए, because we will need to apply these definitions for most questions of differentiability. So differentiability involves one frequently asked theorem, conclusion or deduction. And this is essentially important for fundamental board exams, subjective exams. बट जेई के लिए अगर कोई थियोरेटिकल क्वेश्चंस आ जाए तो ये थ्योरम जानना जरूरी होता है, और एप्लीकेशंस के लिए भी. तो थ्योरम की स्टेटमेंट है, इफ एफ ऑफ एक्स इज डिफरेंशियबल एट एवरी पॉइंट इन इट्स डोमेन, it must be continuous in that domain. So ये थ्योरम कंटिन्यूटी और डिफरेंशियबिलिटी के कॉन्सेप्ट्स के बीच लिंक बना रहा है कि अगर हमने किसी फंक्शन के लिए प्रूव कर लिया कि ये डिफरेंशियबल है इस पॉइंट पर, तो हमें कंटिन्यूटी चेक करने की जरूरत ही नहीं है, क्योंकि डिफरेंशियबिलिटी गारंटीज कंटिन्यूटी. सो दिस थ्योरम इज एक्सट्रीमली हेल्पफुल अगर किसी फंक्शन की कंटिन्यूटी के बारे में कुछ डाउट आ रहा है, पर उसका डेरिवेटिव दिया गया हो कि दैट डेरिवेटिव एग्जिस्ट्स. इम्प्लिसिटली यही इंप्लाई हो रहा है कि वो फंक्शन कंटिन्यूअस भी है. हर पॉइंट पर उसका यूनिक टैंजेंट बनाया जा सकता है, और हर पॉइंट पर लेफ्ट हैंड राइट हैंड लिमिट एफ ऑफ ए से कंकर कर रहे हैं. तो इस थ्योरम का एक छोटा सा प्रूफ देख लेते हैं. ये प्रूफ लिमिट्स के कॉन्सेप्ट्स का ही एप्लीकेशन है और सब्जेक्टिव एग्जाम्स में ही काम आएगा, पर प्रूफ को एक बार देख लेना अच्छा रहेगा टू नो हाउ वेरियस रिजल्ट्स आर डिड्यूस्ड फ्रॉम सिंपल डेफिनेशंस. तो इसका प्रूफ कुछ ऐसे है. आवर एम इज टू शो, हम क्या करना चाह रहे हैं कि the limit as x tends to a, f of x is equal to f of a, and we are given that f dash a exists and is finite. तो हम given से इस पर कैसे आ सकते हैं? The only tool that we have with us for this proof is the definition of the derivative. So let's use that definition. The existence of f of a implies that the limit h tends to 0 of f of a plus h minus f of a by h also exists, right? So let us consider the limit x tends to a, f of x to be equal to f of a. This is what we have to show, right? This can also be written as the limit as x tends to a of f of x minus f of a, क्योंकि f of a का a पे लिमिट f of a ही है. is equal to 0. So instead of proving this, we can also show this. These are both equivalent. Now the limit as x tends to a of f of x minus f of a, if we multiply and divide by x minus a and then split the limits, we are able to multiply and divide by x minus a. If you remember, when we say the limit of a variable at a point, the variable never actually reaches that point. So x minus a is not actually 0. So we are able to multiply and divide by x minus a and then separate the limits as well. Right? Now, we are able to recognize this particular limit, right? We know what this limit stands for, right? ये हमने पहले देखा हुआ है. This is nothing but the derivative of f at a, right? And we are given that the derivative of f at a it exists and is also finite. So hence we can conclude that the value on the left hand side is equal to f dash a into, what can we say about this limit? This limit is by direct substitution 0. So we will put in 0 is equal to 0. So what we found is that essentially the limit as x tends to a of f of x minus f of a is 0, right? So now that we've reached this point, this was what we had to show. This can also be written as the limit as x tends to a of f of x is equal to f of a. And we have shown that given that a function is differentiable at a point, the function must also be continuous at that point. So yeah, that is the proof. Using elementary principles of mathematical reasoning, you might recall that if P implies Q, the negation of Q implies the negation of P. So what this means is, when differentiability, we have proven that differentiability implies continuity. The proof also implies, the proof readily, reduces to the fact that discontinuity will imply non-differentiability, right? और इसका रीजनिंग यही है कि अगर हमने कहा कि जब भी कोई फंक्शन डिफरेंशियबल होता है वो उस पॉइंट पे कंटिन्यूस भी होता है, अगर उस पॉइंट पे कंटिन्यूस ना हो तो डिफरेंशियबल भी नहीं हो सकता, क्योंकि अगर डिफरेंशियबल होता तो कंटिन्यूस भी होता, और हमें पता है कंटिन्यूस नहीं है तो डिफरेंशियबल भी नहीं है. सो दीज आर द टू रिजल्ट्स वी हैव now learned, that differentiability of a function implies its continuity and discontinuity of a function implies its non-differentiability. The converse of this theorem, the converse being that continuity implies differentiability, you will see is in fact not true. Or मान लीजिए true होता that continuity implies differentiability and also implies continuity, then these are equivalent definitions and there would be no need to define a new term, differentiability, right? So that is one way to justify to yourself that continuity is not going to imply differentiability. When differentiability is implying continuity, then they would both be equivalent terms. But let's look at the proof of why the converse is actually not true. So you might be familiar with the idea that to prove that something is wrong, it is sufficient to show one example that does not, hold true with the theorem. That is the proof by counter example. So here, that is the method of proof we will use to show that the converse does not hold. And the counter example we're going to take is f of x is equal to mod x. In the lecture so far, we have found that mod x is continuous at x equals 0, right? Now we have to look at the differentiability of mod x at x equals 0. For that, let's look at the directional derivatives one by one. First being the left-hand derivative. Left-hand derivative, आपको याद होगा, is defined as the limit as h tends to 0, f of a minus h minus f of a divided by negative h. Substituting the value of f of x, we get modulo the limit as h tends to 0 modulo a minus 0 minus h, because the a we're talking about here is 0. We're considering the differentiability of mod x at x equals 0 minus mod 0 0 by negative h. modulus of negative h is absolute value of h divided by negative h, which is -1. Similarly, let's look at the right-hand derivative of mod x at x equals 0. The limit as h tends to 0 of f of a plus h minus f of a divided by h, where a is 0. We're considering differentiability at 0. This can be written as the limit as h tends to 0 of modulo h minus mod 0, which is 0, by h, which is +1. We can see that the left-hand derivative and the right-hand derivative don't agree with each other. And this implies that f dash 0 does not exist. So we have found one example where a function is continuous at a point and not differentiable at a point, which means the converse of the theorem we just stated is not true. Continuity does not always imply differentiability, right? But differentiability always implies continuity. Now let's look at some factors that can cause non-differentiability. इसका यही मतलब है कि क्या क्या चीजें देख के सीधा हम कह सकते हैं कि ये फंक्शन नॉन डिफरेंशिबल है। ऐसे कुछ फीचर्स होते हैं फंक्शंस के ग्राफ के जो जब दिख जाए हम इमीडिएटली कह सकते हैं कि ये ग्राफ इस पॉइंट पे डिफरेंशिबल नहीं है। तो वो कौन से फीचर्स हैं? पहला ऐसा फीचर ये ही है, यूजिंग द प्रीवियस थ्योरम दैट एफ ऑफ एक्स इज डिसकंटिन्यूअस एट एक्स इक्वल्स 0। अगर हमें फंक्शन का ग्राफ देख के दिख जाए कि एफ ऑफ एक्स वहां पे कंटिन्यूअस नहीं है, या तो लेफ्ट हैंड लिमिट और राइट हैंड डेरिवेटिव लिमिट एग्जिस्ट नहीं, अग्री नहीं कर रहे, देयर इज जंप डिसकंटिन्यूटी और एसिम्प्टोटिक डिसकंटिन्यूटी, ऑसिलेटरी डिसकंटिन्यूटी, या मिसिंग पॉइंट है, वहां पे फंक्शन डिफाइन नहीं है, आइसोलेटेड पॉइंट है, तो इन सब फीचर्स को देख के हमें पता चल रहा है फंक्शन डिसकंटिन्यूअस है। एंड यूजिंग द कॉन्ट्रापोजिटिव ऑफ द थ्योरम वी जस्ट प्रूव, अगर फंक्शन किसी पॉइंट पे कंटिन्यूअस नहीं है तो वो डिफरेंशिएबल भी नहीं हो सकता। सो दिस इज वन फीचर वी कैन लुक फॉर व्हेन ट्राइंग टू कंफर्म नॉन डिफरेंशिएबिलिटी कि वो फंक्शन किसी पॉइंट पे डिसकंटिन्यूअस है। तो इस फीचर का ज्योमेट्रिक ऑल्टरनेटिव यही है कि अगर वो डिसकंटिन्यूअस है, लेफ्ट हैंड और राइट हैंड पे वैल्यूज एग्री नहीं कर रही, या वो पॉइंट ग्राफ से अलग हो गया, इसका यही मतलब है दैट वी कैनॉट ड्रॉ अ यूनिक टैंजेंट एट एक्स इक्वल्स a, राइट? ग्राफ अगर दो अलग अलग हिस्सों में बट गया है किसी पॉइंट पे, तो उन दो हिस्सों में हम एक टैंजेंट नहीं ड्रॉ कर पाएंगे, तो इसलिए फंक्शन डिफरेंशिएबल नहीं होता ऐसे पॉइंट्स पे। दूसरा फीचर जो हम देखते हैं नॉन डिफरेंशिएबिलिटी प्रूव करने के लिए, वो होता है द इनइक्वालिटी, द फैक्ट दैट the left hand and the right hand derivatives are unequal, right? And इसका geometric meaning है कि of course here we are considering that both the left hand derivatives and the right hand derivative exist at a, but they are not equal। और इसका आप सोचिए geometric meaning क्या हो सकता है कि लेफ्ट हैंड पे भी और राइट हैंड पे भी हम tangent बना पा रहे हैं, पर उन tangent के स्लोप इक्वल नहीं है। इसका मतलब हुआ कि there are sharp turns in the graph of f of x, right? अगर हम एग्जांपल देखना चाहेंगे, अगर कोई ऐसा ग्राफ दिया गया हो फिर सडनली वो ऐसे कट हो जाता है, तो इस पॉइंट पर हमें दिख रहा है कि एक शार्प टर्न हुआ है, जहाँ की लेफ्ट हैंड साइड, उस पॉइंट के लेफ्ट हैंड साइड पे टैंजेंट का स्लोप पॉजिटिव था, राइट हैंड साइड पे सडनली वो नेगेटिव हो गया। तो इस पॉइंट पर डेरिवेटिव एग्जिस्ट नहीं करता। ये काफी क्रूड एग्जांपल है, पर आइडिया है कि अगर किसी पॉइंट पर ग्राफ शार्प टर्न ले रहा है तो उस पॉइंट पे हम टैंजेंट नहीं बना पाएंगे यूनिक, तो वो डिफरेंशिएबल नहीं होगा। और जो तीसरा फीचर हम देखते हैं वो है कि बोथ f dash a minus and f dash a plus exist and might even be equal, but they are not finite. Of course, when they're not finite, we cannot talk about their equality. But suppose f dash a minus और f dash a plus दोनों का फॉर्मूला कुछ अग्री कर रहा है, सपोज 1/x, तो और उनकी वैल्यूज फाइनाइट नहीं है, दे आर अप्रोचिंग plus or minus infinity. So then we can conclude that the derivative at that point does not exist, or iska geometric meaning hai the the fact that f dash a minus and f dash a plus are not finite. Iska geometric alternative meaning yahi hai ki at that point there is a vertical tangent that has come up in the graph. And when there's a vertical tangent that has come up in the graph, we cannot say that the function is differentiable because we cannot write a value of its derivative. So these are the three factors that contribute to non-differentiability. Number one, we look at whether the function is continuous at the point, and as soon as we find that is discontinuous, we immediately know that it's not differentiable. Secondly, we look at whether the function has any sharp turns on its graph. And third, we look at even if we're able to draw unique tangents, are those tangents parallel to the y-axis? If they are, then again the derivative does not exist, right? So इसका एक application देख लेते हैं. Discuss the differentiability of the function f of x is equal to 2x plus 5 raised to 3 over 5, x equals 5 over 2. तो इसको सॉल्व करने के लिए हम पहले तो फर्स्ट प्रिंसिपल्स की मैथमेटिकल डेफिनेशन लगा सकते हैं कि लेफ्ट हैंड डेरिवेटिव राइट हैंड डेरिवेटिव इक्वल होने चाहिए तभी डेरिवेटिव एग्जिस्ट करेगा. पर लेट्स लुक एट अ ज्योमेट्रिक वे टू सॉल्व दिस क्वेश्चन कि हमने तीन फैक्टर्स देख लिए हैं जो नॉन डिफरेंशिएबिलिटी पे कंट्रीब्यूट करते हैं. तो उन्हीं फैक्टर्स को अगर हम वेरीफाई कर पाए इस क्वेश्चन में तो शायद ये सॉल्व हो जाएगी. पहले तो हम नोटिस करते हैं कि x equals 5/2 is actually the root of this function. तो उसकी वैल्यू इस पॉइंट पर 0 है. जब हम उसके राइट हैंड साइड पे इस फंक्शन की वैल्यू पॉजिटिव है, उसके लेफ्ट हैंड साइड पे इस फंक्शन की वैल्यू नेगेटिव है, और किसी एक साइड पे दिस इज ए polynomial function raised to a fractional power. We can differentiate this function through rules of differentiation that we have learned in the first chapter of calculus. So for x greater than 5 over 2, f dash x will be something of the form 3 over 5 2x minus 5 into 2, 2x minus 5 being raised to negative 2 over 5. तो डेरिवेटिव के एक्सप्रेशन से हम देख सकते हैं कि the variable containing term is appearing in the denominator क्योंकि उसका exponent negative है. That means that as we keep increasing x, the value of the derivative keeps decreasing, right? For all points after 5 over 2, let's put this graphically. For all points after 5 over 2, where the function's value at 5 over 2 is 0, the derivative is positive but keeps decreasing. So something like this. The graph will look roughly like this. Derivative being positive but decreases with x. Similarly, for x less than 5 over 2, again we get the same expression for f dash x. Here we find that again by decreasing x further and further, the magnitude of the variable term keeps increasing, but the variable term appears in the denominator. So the magnitude, the net magnitude of f dash x is going to continuously decrease, right? However, because x is less than 5 over 2, this term is negative and it's raised to an even power divided by 5. So what we get in terms of this graph is the graph is going to look something like this now, right? Because the magnitude of the derivative is again decreasing, just as it was when x was greater than 5 over 2. So, and this is again because the variable term is appearing in the denominator. So as we keep decreasing x, as we keep decreasing the magnitude, as we keep increasing the magnitude of 2x minus 5, the value of the derivative keeps decreasing. Derivative छोटा होता जा रहा है as x tends to minus infinity. जैसे derivative छोटा हो जा रहा है, होता जा रहा है as x tends to positive infinity. So roughly, we can conclude that the graph is going to look something like this, right? At x equals to 5/2, then if the function progressively decreases in its derivative magnitude towards infinity, and again decreases in magnitude towards minus infinity at f of x equals 0, where x is 5/2, इस ग्राफ से दिख रहा है कि इसका tangent वर्टिकल हो जा रहा है, राइट? अगर इसका tangent वर्टिकल हो जा रहा है तो हमारे थर्ड फैक्टर से ये फंक्शन डिफरेंशिएबल नहीं होगा। इसका फर्स्ट प्रिंसिपल के डेफिनेशन से अगर जस्टिफिकेशन देखना चाहें तो we can compute either the left hand or the right hand derivative for this purpose. Let's look at the left hand derivative or the right hand derivative. So the limit as h tends to 0, f of 5/2 plus h minus f of 5/2 divided by h. This is the limit as h tends to 0. F of 5/2 plus h will be h raised to 3/5 minus f of 5/2 is 0 divided by h, which is limit as h tends to 0 of h raised to -2/5. एंड अगर कोई 0 पे टेंडिंग वेरिएबल डिनोमिनेटर में अपीयर करता है, लिमिट की वैल्यू हम इन्फिनिटी लेते हैं, सो वी कैन सी दैट द लेफ्ट हैंड डेरिवेटिव इज नॉट फाइनाइट एंड हेंस द डेरिवेटिव डज नॉट एग्जिस्ट। तो एक अप्रोच था, हम फर्स्ट प्रिंसिपल्स की डेफिनेशंस, मैथमेटिकल डेफिनेशंस लगाएं, जहाँ की दूसरा अप्रोच ग्राफ से था कि अगर हमें दिख रहा है कि इसका ग्राफ कुछ ऐसा दिखेगा कि उस पॉइंट पर उसकी डेरिवेटिव की वैल्यू इन्फिनिटी हो जा रही है, तो directly without writing a single expression we can conclude that is not differentiable at that point, right? Yeah, so that is a good application of the factors that we've studied for non-differentiability. Differentiability के definition और इन examples को देखने के बाद हम एक concept consider करते हैं which is differentiability over an interval. अब continuity over an interval काफी कॉमन कॉन्सेप्ट है, काफी जगह यूज होता है, but this is not such a common concept and not even a very widely accepted concept, because here we're differentiating between open and closed intervals, but we're not differentiating between what it means for a function to be differentiable on those intervals. अगर हम कहें कि एक फंक्शन ओपन a, b में डिफरेंशिएबल है, या हम कहें कि क्लोज्ड a, b में डिफरेंशिएबल है, you will see that it means essentially the same thing for it to be differentiable, except in some cases we apply an additional condition on a and b, क्योंकि हम एक इंटरवल के एंड पॉइंट्स पर डिफरेंशिएबिलिटी नहीं देख सकते. It doesn't make sense to look at the tangent at the end point of a line, right? अगर हमारे पास कोई कर्व है और कोई हमसे पूछे यहाँ पे कर्व टर्मिनेट हो रहा है, हमसे पूछे कोई कि इस पॉइंट पर टैंजेंट क्या है, तो एक अप्रोच है कि लेफ्ट हैंड कर्व से देख के लेफ्ट हैंड डेरिवेटिव के अकॉर्डिंग टैंजेंट बनाए, बट दिस इज नॉट मैथमेटिकली करेक्ट बिकॉज वी डोंट नो व्हाट लाइज टू द राइट ऑफ दैट पॉइंट, राइट? सो वी कैन नॉट कंक्लूड एक्चुअली वेदर it has a tangent at that point even or not. So and one additional thing to consider when you have a graph and you're drawing a tangent at its end point, you have no reason not to draw the tangent like in any direction, any arbitrary direction, because that point has nothing to its towards one end. So you can assume any direction for its tangent towards the right. So what is commonly accepted as the definition of differentiability over a closed interval a, b is number one, it is differentiable at all points belonging to open a, b, and second, it is continuous at the endpoints. Because of course, if a function is not continuous at a point, it's definitely not differentiable. So just to consider the endpoints into the definition of differentiability over an interval, we impose an additional condition that the function is continuous at a and b, because that is the minimum condition it must satisfy to be differentiable. Once we know that the function is continuous at a and b, we assume that it must also be differentiable. Although continuity, of course, does not imply differentiability, but for our purposes, we conclude that the function is differentiable at x equals a and x equals b as long as we're able to prove that it's continuous at x equals a and b. All right. So using what we've learned so far, these concepts can be applied to the various common functions that we study in math, which are polynomial, trig, exponential, logarithmic, rational, etc. So for these functions, in particular for these functions, we find that they are differentiable for all points in their domains. The common functions that we encounter so frequently in maths are in fact differentiable in their domain. So we need not evaluate the condition for differentiability for these common functions. We can, in problem solving, we can just keep in mind that as soon as we see a polynomial or rational function or a trigonometric function, uh, a trigonometric function alone, not a combination of these functions. Because then we'll have to, evaluate further conditions if there's, for example, sine 1 over x or any combination of two functions that's appearing. If there's a standalone function, standard function that we see among these functions, then we can immediately conclude that it is differentiable over all points in its domain. We did not check for its differentiability. So it's pretty helpful to keep this fact in mind. Let's look at another example. Let's discuss the differentiability of sine x square over x when x is non-zero and 0 when x is 0. So here we're going to use again the first principles to solve this question. Let's consider the left-hand derivative. The left-hand derivative would be the limit as x tends to 0 minus of f of x minus f of a, which is f of 0, which is 0, divided by, of course, x. So what this boils down to is limit x tends to 0 minus sine of x square over x square. And from the chapter of limits and derivatives, we know that this evaluates to 1. Whenever there's like sine of f of x over f of x, where f of x tends to 0, we obtain 1. Similarly, from the right-hand derivative, we have the analogous steps, sine of x square over x minus 0 over x, which is the right-hand limit at 0 of sine x square over x square, which is again 1. So we see that the left hand and the right hand derivatives concur, and therefore the derivative exists at x equals 0. But the question was to discuss the differentiability of this function in general. Why did we only consider x equals 0? Because looking at the function for all non-zero x, we can sort of conclude that it is differentiable. Like, we get the intuitive feeling. Of course, we can verify through limits, but what we see is that sine of x square over x is not going to pose any issues in terms of its finiteness, right? X becomes 0 only at x equals 0. So the denominator is not going to pose any challenges for us for points other than 0. Sine of x square over x can be considered a standard continuous function for our purposes and differentiable at all points other than 0. Only 0 was, the point that sort of, seemed a suspect of non-differentiability. So that is what we evaluated. If this were an objective question, I would immediately write that for all non-zero points, the derivative exists, and for 0, I would solve it. However, if it is a subjective question, of course, you'll have to show using left-hand derivative, right-hand derivative for an arbitrary point a not equal to 0, why f of x is differentiable. Right? So yeah, this is the next concept is differentiability of piecewise functions. So for this concept, let's look at an example first, and then we'll discuss what procedure we're actually following. So let's take the piecewise function. You must remember what a piecewise function is from the first chapter of calculus because we encountered it so often. A function that is broken at a particular point in its domain and divided into two different functions about that point. In this question, what we have to do is find b and c such that f of x is differentiable at all points in its domain. Again, from our standard result, these are both polynomial functions around 1. We need not bother about their differentiability at points other than 1 because they will be for sure differentiable just by looking at them. Of course, again, if it's subjective, then we have to show why they are differentiable. But for objective questions, we know that polynomial functions or their combinations are with trigonometric functions or exponential logarithmic functions, as long as they don't appear in the denominator, are going to be differentiable. So the solution for this would comprise of evaluation of differentiability at x equals 1. For this piecewise function on the left-hand side and the right-hand side, we know it's differentiable. At every point, we also know what the derivative is, right? For all points less than 1, the derivative f dash of x is 1, right? And for all points to the right of 1, how I got this one is by elementary principles of derivative d by dx of x is 1. The derivative for all points greater than 1, again, we apply rules of differentiation. F dash x would be 2 times x plus b, right? And using these derivatives around 1, it is reasonable to conclude that at x equals 1, because it falls in the first branch, and the left, if x were to be, if f of x were to be differentiable at x equals 1, its derivative would equal the left-hand derivative and the right-hand derivative, right? If the derivative exists, it would be equal to the derivative on the left-hand side and the derivative on the right-hand side. If that is the case, these must also both be equal. That is 2x plus b equals 1 at x equals 1. And therefore, 2 plus b equals 1, which means b is equal to -1. Right? This is all good. We found the value of b. What about the value of c? Here we use, the theorem that we were talking about earlier, that differentiability implies continuity. So assuming that the function is differentiable at a point 1, we got the value of b. This gives no information about the value of c. To find the value of c, now we'll apply the continuity constraint. So for continuity, if you remember piecewise functions, we directly substitute the value of the breaking point. Here the breaking point is 1. On the left hand side of the function, this value is to 1. Putting x equals 1 into x gives 1. On the right hand side, this evaluates to 1 plus b plus c. We know the value of b is -2. So c is equal to 1. So using the definition of differentiability and using the fact that differentiability implies continuity, we found the values of b and c. The alternate way to solve this question is to use the left-hand derivative and the right-hand derivative. And if you use that, you will find that b and c are simultaneously found, because essentially both differentiability and continuity are incorporated into that condition of left-hand and right-hand derivatives, if you think about it. How did we prove the theorem that differentiability implies continuity? Using the left-hand and the right-hand derivative. So uh, this is one intuitive way of solving objective questions, where they've broken it into two piecewise, branches. And in each branch, we know what the derivative is. At the breaking point, we will just equate those two derivatives and impose conditions of continuity. So this is one quick way of solving this question. The correct subjective way of solving this question would be to find the left hand and the right hand derivatives and equate them. Right. So to summarize, what we're really doing for piecewise functions is, number one, we're applying the derivatives on each branch. And number two, which we will see in further examples in the next lecture, is we're looking at the graphical conditions, the geometrical conditions. Yeah, so these are the essentially two things we're going to do for piecewise functions. And this is it for today's lecture. What we looked at today was firstly the intermediate value theorem, and then we went on to consider various aspects of differentiability, conditions for differentiability, applications of the definition of differentiability over an interval, and finally we concluded with piecewise functions. In the next lecture, we'll start again with piecewise functions, and then look at a few questions and examples relating to this topic. Thank you for paying attention today, and I'll see you in the next lecture.